Hello, hi students. So this is Perricyclic reactions part 3. Today in this lecture we are going to see symmetry aspects of molecular orbitals and nodes, HOMO in the case of ground state and HOMO orbitals in the case of excited state, that is HOMO in thermal condition and HOMO in photochemical condition. So let us start with the molecular orbital. Two types of symmetry properties we use to understand pericyclic reactions, or while drawing molecular orbitals, especially pi molecular orbitals in a conjugated pi system or simple alkene, that is plane of symmetry and C2 rotational axis of symmetry. This plane of symmetry is mirror plane of symmetry M, are shown as sigma, and we consider a rotation by 180 degrees along one of the axes. Therefore, it is a C2 rotation axis of symmetry. So let us see these two operations in a simple atomic molecular orbitals. Like a psi1 molecular orbital of ethene. In this, let us do these two operations, that is plane of symmetry and C2 rotational axis of symmetry. Any plane that is imaginary usually, which bisects the molecule or which divides the molecule into two equal halves. If such plane is present in that molecule or in that species or in that object, we call that plane of symmetry is there in that molecule. Here in this case, ethene, that you can see CH2 double bond CH2, its molecular orbitals are psi1 and psi2. The psi1 molecular orbital having 0 nodes, because n is equal to 1 here, 1 minus 1 is 0, that is calculation of number of nodes we have already seen. For a psi1 orbital, number of nodes is equal to 0. So with 0 nodes, you can represent that one as plus amplitude with plus amplitude, or maybe red lobe with red lobe. So this is a sigma bonding orbital, you can say. So it is plus and plus, red with red, blue with blue. That's how it's going, isn't that? So then this is your psi molecular orbital, psi1 molecular orbital. So in that, this is the plane that we are speaking of. This is the plane. So where that is the blue line that you can see. So this is the blue line that you are looking at. So this is a molecular orbital psi1, and here this is positive side, you can imagine, negative, positive and negative, red, blue, red, blue, red is on the same plane. So you can say that it is a bonding. And if you keep a mirror plane here, this line indicates a mirror plane, then what happens? This reflection is same as this one. So you can bisect this molecular orbital along this plane. So obviously it is symmetric with respect to plane of symmetry. So sigma, it is symmetric, you can say. Its mirror image would look like this, isn't that? So that's how psi 1 with respect to plane of symmetry, it is symmetric, you can say. And now coming to it's psi 1 with C2, that's your psi 1 molecular orbital. This one you are trying to make a C2 rotation. If you make a C2 rotation, then what happens? On C2 rotation means at 180 degrees if you rotate, what happens is this blue will flip upside, so and red will come downside. So that's how it comes. And whatever new arrangement that you got is not identical with your original. If it is not identical with your original on rotating 180 degrees, then you can say this both are not identical, so you can say it is asymmetric. So with respect to C2 rotation, what happens? The psi 1 molecular orbital is asymmetric, whereas with respect to mirror plane of symmetry, that is sigma, it is symmetric. Okay. Now let us see a psi 2 molecular orbital. So how would a psi 2 molecular orbital can be drawn? Psi 2, which means number of nodes is equal to 2 minus 1, that is we know the formula n minus 1. So n minus 1 is equal to 2 minus 1, that is 1. With one node, how can you draw that one? So which looks something like this. This is the node, that it is dot is the node, blue with red, blue with red. So which means this is a node, this is a node, and this is not a node. Here red to red is a overlapping and it is bonding, and this is a anti-bonding with a node, you can say. So if there is a node, what you can say, and now you just make a C2 rotation. In psi 2 molecular orbital, you make a C2 rotation. If you make a C2 rotation, then what happens? It results in what? Rotating something like this. So you can I can even rotate this one. So here C2 rotation along the plane will give you something like this. Okay. So it's a symmetric with respect to C2. It is a symmetric, you can say. So along this you hold this one and simply rotate. So then what happens is it looks on rotation, you may get something like this, isn't that? That's what the rotation is. That's the rotation operation I have carried out. So you can further rotate this one, so you'll get the same, isn't that? So on C2 you are getting what? A symmetric psi 2 orbital you are getting. And now coming to a psi 2 with sigma, this is m sigma you are trying to carry out. The blue line indicates the mirror plane, so carry out that sigma operation. So what happens? Blue won't reflect like a red. So what you can say is it is asymmetric. It is a asymmetric. So that's how you can say psi 1 orbital is symmetric with respect to sigma and asymmetric with respect to C2. Psi 2 is reverse of psi 1, that is C2 asymmetric and sigma symmetric. Sigma symmetric. So from this, let us generalize one thing. In general, odd number of molecular orbitals such as psi 1, psi 3, psi 5 are symmetric with respect to sigma, plane of symmetry, and asymmetric with respect to C2, rotational axis of symmetry. I repeat it again, that in general, odd number of molecular orbitals, odd means psi 1, psi 3, psi 5 are symmetric with respect to plane of symmetry, sigma, and asymmetric with respect to C2. And even number of molecular orbitals, if psi n, where n is even number, if it is psi 2, psi 4, psi 6 are asymmetric with respect to plane of symmetry and symmetric with respect to C2, rotational axis of symmetry. From this you can put it like this, that molecular orbitals that are symmetric with respect to C2 are asymmetric with respect to sigma or plane of symmetry. If C2 is present, plane of symmetry is absent. If plane of symmetry is present, C2 is absent. If one is present, the other will be absent. That is, plane of symmetry if present, C2 will be absent. If C2 is present, plane of symmetry will be present. Okay, so if with respect to one of the symmetry aspect, that is C2, if it is present, sigma will be absent. If sigma is present, C2 will be absent. So that's how you can generalize that. So let us see the molecular orbitals and symmetry in ethylene. So ethylene molecular orbitals. So how many carbons you are having? 2 carbons you are having. Between 2 carbons you are having a pi bond. So obviously the number of atomic orbitals that you use is 2. So you need to represent that one with 2 lobes. Okay. So now here you can imagine one as a red one is plus lobe, blue one is minus lobe. Here also red one plus lobe and minus lobe. Positive amplitude and the negative amplitude as it is wave function, you can say. So its electronic configuration is written as it is 2 electrons, psi1 2, psi2 0, psi1 2, psi2 0. So psi1 is lower energy, psi2 is a higher energy. So lower energy orbitals gets electrons first, and then higher energy orbitals will get electrons. So you have how many electrons? Pi electrons, 2 electrons. So you'll fill orbitals with 2 electrons each. So making that one as psi1 2, no more electrons. So psi2 becomes as a 0. So going for an energy profile, energy diagram of that one. So psi1 with lower energy and psi2 with the higher energy. So now coming to how to draw psi1 molecular orbital. Psi1 molecular orbital will be with 0 nodes and psi2 will be with 1 node because n minus 1 formula. So 1 minus 1 is 0, 2 minus 1 is 1. So your notation itself is indicating psi2 is having 1 node, psi1 is having 0 nodes. With 1 node you can write that one as a plus lobe with a plus lobe. Red is overlapping with red, blue with blue, so it is 0 nodes here. And in the case of psi2, blue with red. So obviously this is a node. This is a node which you can see as a dot there. That's a node it is representing. Okay. Now coming to fill its electrons, psi1 is having 2 electrons, psi2 having 0 electrons. Psi2 having 0 electrons. So now which orbital is having electrons? Psi1 having electrons. So this becomes as what? Your HOMO. Here your HOMO and LUMO. You just try to identify that. So highest occupied molecular orbital is psi1 with 2 electrons, and least unoccupied, least in terms of what? Energy, least in terms of energy, which is unoccupied? Psi2 is unoccupied. So your psi2 becomes as what? LUMO. If at all there is an excited state, this is the ground state configuration with psi1 having 2 electrons and psi2 having 0 electrons. If at all there is an excited state, your electron will jump from psi1 to psi2. One of the electron will jump from psi1 to psi2 as that you can see. That's how it jumps. So if electron jumps, what happens? Psi1 to psi2 electron will move, and now this will become as your new HOMO. Okay, so when electron is jumped from psi1 to psi2, then one electron will be there in psi2, making that one as psi1 is having 1 electron. If that is having 1 electron, what happens? That is highest occupied molecular orbital. So if that is highest occupied molecular orbital, then your LUMO will change. Okay, so that's how you should understand. And now coming to this one, symmetry. So what about your symmetry criteria? Your psi1 is what? Odd number of orbital. So simply by even looking at also you can say it is symmetric with respect to sigma, and with respect to C2 it is asymmetric. And the same reverse will be for what? Psi2. Psi2 is what? Sigma asymmetric, and C2 symmetric it becomes as. Isn't that? So that's how, just to sum up, your psi1 having 0 nodes, psi2 having 1 node, psi1 configuration with psi1 2 electrons, psi2 0 electrons, psi1 is HOMO, psi2 is LUMO in ground state. In excited state, electron will jump from HOMO to LUMO. Now your new HOMO will be what? Psi 2. New HOMO will be what? Psi 2. That you should keep it in mind. Very important aspect. Electron will shift from where to where? From psi 1 to psi 2. Then highest occupied molecular orbital will be your psi 2. That happens in excited state. So anyway, we'll see that also in the coming class. Okay, see that's one. Just to put up, in the case of ethene, that's how this is 0 nodes, this is 1 node, psi 1 with 0 nodes, psi 2 with what? Psi 1 with 0 nodes, psi 2 with 1 node, you can see, and 2 electrons in the case of psi 1 and 0 electrons in the case of psi 2 with respect to C2. Psi 1 is what? Asymmetric, and sigma symmetric. Your psi 2 is what? C2 symmetric, sigma asymmetric. Okay, so summed up like this: molecular orbital, sigma operation, C2, plane of symmetry, and C2 rotational axis of symmetry. Your psi 1 is sigma symmetric, C2 asymmetric, psi 2 is sigma asymmetric, and C2 symmetric, you can say, isn't that? So let us see one more. In the case of 1,3-butadiene, 1,3-butadiene. So here CH2 double bond CH, single bond CH, double bond CH2 is your 1,3-butadiene. Here in this case, how many pi bonds are there? 2 pi bonds. Between 4 carbon atoms, you are having 2 pi bonds. So we require 4 lobes or 4 orbitals to represent 1,3-butadiene, isn't that? So 2 pi bonds. 1 pi bond we have represented with 2 lobes. Now 4 pi bonds. So how to draw that 4 pi orbitals? So that orbitals are like this. So in this case, we already know that psi 1 having 0 nodes, psi 2 with 1 node, psi 3 with 2 nodes, and psi 4 with 3 nodes, which you can see as straight lines in between, isn't that? So look at that psi 1, a blue lobe overlapping with blue, blue with blue, blue with blue, all plus upside and all minus downside. So it is what? 0 nodes. This is bonding, that is also bonding. Okay, and now coming to psi 2 lobes. How will you draw that psi 2 lobes? See, blue with blue bonding, blue adjacent to green node, it is a node, and now coming to green next to green, this is a bonding, that is a bonding, isn't that? Now coming to psi 3, will have how many nodes? 2 nodes, blue green node, green green bonding, and green blue node. Psi 4, blue green, green blue, blue green nodes. So in between you are having what? Nodes. Those are the nodes, and these nodes are also symmetrically arranged. You can't arrange these nodes somewhere like this, one to next, first you can't have node. They are also arranged symmetrically. You just look at, if one node is there, it is at the center. If 2 nodes are there, they are at a left and right. If 3 nodes are there, they are consecutively, they are also arranged symmetrically, isn't that? So that's how the nodes are present. And then now coming to psi 1 with 2 electrons, psi 2 with 2 electrons. So psi 3 with 0 electrons, and psi 4 also with 0 electrons. So least unoccupied orbital, least unoccupied molecular orbital is psi 3. Least in terms of what? Energy. Least in terms of energy. Least unoccupied molecular orbital is psi 3, and highest occupied molecular orbital is psi 2. Highest, the name itself is suggesting highest in terms of energy, occupied means having electrons, molecular orbitals. So that psi 2 is having 2 electrons, so we call that one as HOMO, and psi 3 is having no electrons, so we call this one as a least energy orbital with unoccupied. Psi 4 is also unoccupied, but psi 3 becomes what? Least unoccupied molecular orbital, and psi 2 becomes highest occupied molecular orbital. Now this is ground state. So excited state, how will you write its excited state? Tell me. one electron will shift from psi 2 to psi 3. If one electron shifts from psi 2 to psi 3, then what happens? You will get a new configuration with the psi 1 2 electrons, psi 2 1 electron, psi 3 1 electron, and psi 4 0 electrons. I repeat it once again. In excited state, electron will jump from where to where? Psi 2 to psi 3. How many electrons? One electron will shift. Now the nomenclature changes. If one electron is shifting from here to here, this becomes your new HOMO and this becomes your new LUMO. Psi 3 becomes new HOMO and psi 4 becomes a new LUMO. That we should keep it in mind. Okay, your psi 3 becomes a new HOMO and psi 4 becomes new LUMO. In what state? In excited state. In excited state. So when electron is jumping from psi 2 to psi 3, this happens in photochemical condition or in presence of a light. One of the electrons shifts from psi 2 to psi 3, then LUMO gets 1 electron. This psi 3 will get 1 electron and psi 4 having 0 electrons. This psi 3 with 1 electron will become new HOMO in photochemical condition, and psi 4 becomes new LUMO in photochemical condition. Keep that in mind. Okay, now let us do these operations. What sigma and C2 operations on these lobes. So look at that psi 1. Psi 1 is keep a mirror plane at the center. Then it is what? Mirror images are there. So obviously symmetric with respect to sigma and asymmetric. So along one of the axes, if you simply rotate C2 180 degrees, green will go up and all blues will come down. Then what happens? It is asymmetric with respect to C2. And similarly, here in this case, symmetric with respect to C2, you rotate exactly, you will get these blues will come over here and these blues will come over here. So obviously symmetric with respect to C2 and with respect to sigma, it is asymmetric. Similarly, the same operations here, symmetric, keep exactly over here a mirror plane. This is same as this one. So obviously symmetric with respect to mirror plane or sigma, and with respect to C2, if you rotate, what happens is this green will come over here. So obviously it is asymmetric with respect to C2. Now look at this one, mirror plane, asymmetric. You keep a mirror over here, what happens? Green won't look like blue. Mirror in the middle you should keep, not somewhere. So then green won't look like blue. So obviously asymmetric with respect to sigma. If it is asymmetric with respect to sigma, then it is symmetric with respect to C2. But anyway, if you go for operation also, if you rotate from here, what happens is blue will come exactly over here. This blue will go over here. So that is C2 symmetric, you can say. That's how you can verify the symmetry operations in the case of 1,3-butadiene pi molecular orbitals. Okay, so simply keep that in mind. First, always the psi 1 molecular orbital is symmetric with respect to sigma, then obviously asymmetric with what? C2. Then you can apply the same to the rest. So just to put up sum up symmetry properties in molecular orbitals of 1,3-butadiene. So starting from psi 1, psi 2, psi 3, psi 4, if odd number of, you can see all the odd ones are having what? Symmetric with respect to sigma and asymmetric with respect to C2. Psi 1 and psi 3, look at odd ones are symmetric with respect to sigma and asymmetric with respect to C2. And even number are psi 2 and psi 4, which are asymmetric in terms of what? Sigma, and symmetric in terms of C2. That's how all your molecular orbitals are designated in the case of 1,3-butadiene and their symmetry operations. Okay, this he would ask you draw the molecular orbitals of 1,3-butadiene and represent the symmetry. All that you can write, and ground state and excited state also you can draw there itself. So then allyl radical. Allyl radical is CH2 double bond CH with the CH2 dot. That allyl radical is having, so this radical is also considered as what? One of the pi molecular unhybridized orbital will having 1 electron here. This CH2 at the end is having what? Unhybridized orbital carrying 1 single electron. This anyway, this is just like our ethene molecular orbital, pi bond is there. So you'll have 3 orbitals here. Total how many? This allyl radical carrying 1 electron, and anyway pi bond represents 2 pi molecular orbitals. So let us see that one, how to draw the molecular orbitals in the case of allyl radical. So 3 molecular orbitals are there. So you'll have psi1, psi2, psi3, and one will have 0 nodes, 2 will have 1 node, 3 will have 2 nodes. Okay, so that's the criteria. Let us see in increasing order of energy. On an energy axis, you can represent psi1, psi2, psi3. See, here in this case, we have represented that one in terms of what? Plus lobes and minus lobes. So now tell me, psi1 is having 0 nodes, plus, 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 plus. So 0 nodes here. Okay, so that's bonding molecular orbital. And psi2 will have how many nodes? 1 node you'll have, which you represent as a, in central one you represent as empty, plus and minus. This is 1 node. And your psi3 is having how many? 2 nodes. So 2 nodes, plus, minus, minus, plus. You can see plus, minus, minus, plus. So how many it is? 2 nodes are there. 2 nodes. Plus amplitude, minus amplitude, minus amplitude, plus amplitude. Amplitude is wave function, one of the wave function. There it is. So that's how you can represent. So nodes are psi1 0 nodes, psi2 1 node, psi3 2 nodes. Node is what? Where the probability of finding electron density is least. So if plus is overlapping with minus, then it is a node, and if plus is overlapping with plus, it is a bonding. So now its configuration, ground state configuration is what? 3 electrons are there. So psi1 having 2 electrons, psi2 with 1 electron, and psi3 with 0 electrons. You can see that psi1 having 2 electrons, psi2 with 1 electron, and psi3 having 0 electrons is your electronic configuration in ground state. So now from this you identify HOMO and LUMO. HOMO is highest occupied molecular orbital, and LUMO is a least unoccupied molecular orbital. So occupied molecular orbital with highest energy is what? HOMO. So this is your HOMO and this is your LUMO. Least unoccupied, the word unoccupied you should understand. Unoccupied means not having. Least unoccupied is what? LUMO. But here psi1 and psi2 are occupied, and this is unoccupied. So whatever you are left with unoccupied is psi3. Okay, and now in excited state, what happens is one of the electrons shifts from psi2 to psi3. Psi2 to psi3 it changes. So this is the shift that you can see. So now this your psi3 becomes as what? In excited state, psi3 having 1 electron will become HOMO. Okay, highest occupied molecular orbital it becomes as. That you should keep it in mind in the case of excited state or in photochemical condition. When one of this electron jumps from psi2 to psi3, this becomes as your HOMO, that is psi3 with 1 electron. Okay, so just to sum up, in the case of LL radical, molecular orbitals are psi1, psi2 and psi3. Symmetry condition is with psi1 is always symmetric with respect to sigma and asymmetric in terms of C2, and psi2 is reverse of psi1, asymmetric with respect to sigma and symmetric with respect to C2, and psi3 is reverse of C2, symmetric with respect to sigma and asymmetric with respect to C2. So that's how your molecular orbitals in LL radical are. Even you can verify how it is. So make one of the operations there. So then you will get what? Molecular orbitals with symmetric operations like that. Okay, so have a look at. And after this one, we are going to see photochemical reactions and thermal reactions, how they are different from each other. So as the name is suggesting, thermal reactions are such reactions which are mediated in terms of in heat, and photochemical reactions are reactions which are carried out in light. So light mediated reactions and photochemical pericyclic reactions we are going to see in the next class. Okay, so let us see that one. Anyway, thank you, and keep solving problems based on this one. Okay, so they will usually ask draw the molecular orbitals diagram of 1,3-butadiene and ethene and LL radical. That they usually ask question. So keep practicing that. Thank you.